Hello everyone and welcome to our IROS 2021 presentation on a structured approach for the co-design of embodied intelligence. My name is Gioele Zardini and this is a joint work with Dejan Milojevic, Andrea Censi and Professor Emilio Frazzoli. This work is sponsored by ETH Zurich, EMPA and the Swiss National Science Foundation through NCCR Automation. This work addresses some of the pain related to the engineering of complex systems. If you think about it, the design of an autonomous robot involves many different building blocks, such as perception, control, planning, energetics, and communication. These components range from hardware to software, and having a good understanding of the whole system is very difficult. In particular, we lack a formal theory to optimally co-design heterogeneous systems. In this work, we tackle the issue by proposing a methodology to deal with the co-design of autonomous robots. The proposed approach is very intuitive and provides rich modeling capabilities, including analytic models, catalogs, and open-loop simulations. Furthermore, the compositionality and modularity of the proposed formalism allow interdisciplinary collaboration and provide actionable information for practitioners to reason about their problems. The proposed approach is based on a monotone theory of co-design, which defines a design problem through three spaces. First, the implementation space, which represents the design choices, the options we have. Second, the functionality space, which represents our objectives, what we need to achieve. And finally, the requirement space, which describes the resources we need to provide the functionalities. Typically, you can understand functionalities as something you want to maximize, and resources as something you want to minimize. In this framework, we model both spaces as partially ordered sets. Since this is not a common concept, let's first define partially ordered sets. A partially ordered set is a set P together with a partial order, which is defined as a reflexive, transitive, and antisymmetric relation. A typical example of partially ordered sets used in design are total orders. For instance, you might describe your energetic cost with the ordered positive reals, or the number of robots in your fleet with the ordered natural numbers. However, posits give you a lot more flexibility. In this work, among others, we will use, for instance, a partial order on positive semi-definite matrices to order uncertainty covariance matrices when controlling a robot. Also, we will use a partial order on different sensors. By considering the use case depicted on the right, in which a vehicle needs to detect a pedestrian, we can characterize any sensor through a false positive rate, a false negative rate, and an accuracy curve. Based on these three curves, we can order sensors using curve dominance. In other words, if the curves of a sensor always dominate the ones of another, then one can say that one sensor will dominate the other. We can formally define design problems with implementation. These are composed by the functionalities and resources posets, F and R, the implementation space, I, and two maps, prov and rec, mapping an implementation to the functionality it provides and the resources it requires. We represent design problem with implementation with the following formal graphical notation. Functionalities are green continuous wires on the left, and resources are dashed red wires on the right. Implementations are hidden. Think, for instance, about the design problem of a battery. Functionalities are the capacity and the maximal provided current, and resources are the cost and the mass. Implementations, instead, are the different battery models which you can find on the market. Now, for the purpose of design, we need to know how something is done. However, for the algorithmic solution of co-design problems, we will forget for a moment about implementations and focus on feasibility relations. A feasibility relation is a map from the product of the functionality space with inverter ordered and resources to bool, the poset containing only the elements false and true. Each pair of functionalities and resources is mapped to true if there exists an implementation providing at least the requested functionality, requiring at most the proposed resources. This is a monotone map, since lowering the functionalities will not require more resources, and increasing the resources will not provide less functionalities. The cool thing about feasibility relations is that we can compose them together in many ways. When composing design problems in series, the semantics is that the resources required by a first design problem are provided by a second design problem. Furthermore, we can have design problems in parallel, and we can model feedback when resources are fed back to become functionalities again. Finally, we can choose between two options, or ask two design problems to hold at the same time. Interestingly, design problems are closed under composition, meaning that any of the mentioned compositions will return a design problem. This is a very useful tool when decomposing large problems into smaller subproblems, and will be very important when co-designing a whole robot. Now, given a composed co-design problem, there are two main queries we want to answer. First, by fixing the desired functionality, we want to find design choices minimizing the needed resources. Dually, we can fix the resources we can spend and maximizes the functionalities we can get. In both cases, we can retrieve the optimal design solutions. We will now focus on the first query. Technically, we are looking for a map H from the functionality space F to the upper set of feasible resources. Practically, this will be a map from the functionality space to anti-chains of minimal resources. We won't go into the details of the optimization, but we want to notice that the described query gives a family of optimization problems in which you have a functionality chosen by the user and you want to minimize the needed resources. Such problems are a particular case of multi-objective optimization problems, which are not convex or differentiable, not continuous, and not even defined on continuous spaces. Now, given the map H for each design problem composing a bigger co-design problem, we can recursively find a map H for the entire diagram, relying on the different composition operators. The minimal set of resources can be obtained as a least fixed point of a monotone map in the space of anti-chains. Now, the introduced theory can be leveraged to propose a structured approach to model and solve embodied intelligence co-design problems. In this work, we consider the proxy of autonomous vehicles design from the perspective of developers, and look at a proof-of-concept example. Nevertheless, this methodology can be applied to other autonomous systems. The proposed modeling approach consists in 4 phases. First, one needs to identify and parameterize the task the robot needs to accomplish. Second, one proceeds with a functional decomposition of the system. The decomposition proceeds until we find components which have precise scope. This can be both hardware and software. Finally, one finds the common resources. For instance, in robotics, these are usually size, weight, power, computation, and latency. Once the modeling part is over, one can implement a skeleton of the model via the developed formal language. This skeleton will encapsulate the dependencies identified in the functional decomposition. Finally, one can fill in the holes by specifying the different components via catalog, analytic models, and simulations. So let's start applying these concepts to robotics. Usually, embodied intelligent tasks can be characterized as a design problem, in which the functionality can be measured through a function-specific performance, for instance, the time needed to solve a task, and the robustness to a specific environment. Solving the task, however, usually requires resources such as cost, power, computation, and mass. Now, if a functional decomposition gives us multiple subtasks, one can interconnect them and jointly consider the total resources needed. Interestingly, composing tasks returns tasks, so this is a compositional property. For the specific case of urban autonomous driving, one can look at the task of following a specific lane. This task can be further decomposed into the one of lateral control, which usually means maintain a specific lane position, and longitudinal control, which can be understood as braking in front of obstacles. Alright, so now following the modeling approach, we need to find components. To do so, we need to distinguish between data flow and logical dependencies. In robotics, we are used to think about data flows, right? A sensor produces sensing data. The data is transferred to an estimation algorithm, which produces a state estimate, which is used by a controller, which will produce some command. To find the co-design components instead, one has to think about logical dependencies. Decision-making requires state estimation, which requires sensing data, algorithms, and computation. Specifically, sensing data requires a sensor, and computation requires a computer. If we apply this procedure to the case of an autonomous vehicle, we get this co-design diagram. Essentially, we have a vehicle to be automated, its automation, a computing unit, some performance metrics such as discomfort and danger, and all these components are interconnected using functional decomposition. In this diagram, the computing unit can be thought of as a catalog of different existing computers, characterized by the computation they produce and the cost, power, and mass they require. Similarly, vehicles and discomfort models can be organized in catalogs. The two control blocks, instead, can be exploded into more precise models, which, again, can be modeled as design problems. Now, the case of lateral control is an example of closed-form simulations. Here we have a lane controller, which we model using LQG control, which needs to operate at a certain frequency, requiring specific observations and producing specific tracking error and control effort. Observations arise thanks to lane cameras, which send data to a feature extractor, which processes the data for the controller. If you wish to know more about modeling linear stochastic optimal control problems as design problems, and so understanding more this lateral control part, check out our ECC 2021 dedicated paper. Via longitudinal control, we wanted to show you a case in which no closed-form solution is available. Specifically, this is a partially observable MDP, in which a brake control module receives measurements from a longitudinal sensing unit, whose performance depends on the environment. The brake control unit can be modeled via simulations, and sensor and algorithms can be put again into catalogs. Now, the interconnection of all these design problems forms a co-design problem, which we can solve with the introduced tools. We can then code these models with a formal language, which is very intuitive to use, and we can solve them using the MCDP solver. Okay, now, given the described interconnected model, we get a design problem, which has the vehicle range, capacity, achievable speed, and robustness to specific environments as functionalities. The resources are subdivided into two classes. First, we have costs, both fixed and operational, externalities, safety, and discomfort. These resources are not fed back. Second, we have resources which are fed back, and which determine the complexity of this kind of optimization problems. These are the computation needs, the mass of the system, the total power, the system noise, and the latency. Now it's time to see this optimization at work and to see some practical results. In particular, we want to look at the minimal resources needed to provide some fixed functionalities. We look at the vehicle cost and discomfort index, which is a proxy for how smoothly does the autonomous vehicle drive. First of all, if you are willing to solve such a complicated problem, usually there is no single solution. Indeed, our framework produces a Pareto front of incomparable optimal ones, which helps designers reasoning about their problems. For each one of these optimal solutions, we can extract specific implementations, including insights both at the hardware and software level. These include the model of the vehicle, the chosen lateral and longitudinal sensors, the computing unit, the frequency update of the controllers, and the specific algorithms that were used. Note that we can also see monotonicity in action. Indeed, in the picture, you see that by increasing the specific desired achievable speeds for the autonomous vehicle, the Pareto fronts described in the minimal resources dominate each other. Alright, so we got at the end of this talk, and it's time to restate the takeaways. We have seen how, using co-design, it is easy to formalize the design of robots all the way from sensor selection to control and perception algorithms. The modeling approach is very intuitive and allows one to include simulation-based, catalog-based, and analytical models in the design. The approach allows interdisciplinary work. While on one hand it is true that we did all of this, the same modeling exercises would have been possible among different teams. After modeling the problem, one can directly solve specific desired queries, producing actionable information for designers. In the future, we would like to include the co-design of a robot into the co-design of fleets of robots and showcase another level of compositionality. Furthermore, we would like to exploit the framework to explicitly look for energy and computation-aware design solutions. This is a new topic, and we are really in the middle of the evangelization process. This includes writing a book, teaching classes, both at ETH and internationally, and organizing international workshops. If you wish to know more, check out the listed web pages. Thank you very much.